So, good evening and welcome to Fundamentals of Micro and Nanofabrications, Week 1 of the live interactive session. The course is being taken by Professor Sushovan Avasti and Professor Sankar Selvaraja from ISC Bangalore, and I am the teaching assistant Vikas Pandey from IIT Jodhpur. Okay, this is a brief about me. I am a PhD scholar at IIT Jodhpur in space science and technology. I have a background in VLSI. I'm taking VLSI, BTech in electronics. I have worked as research and development engineer, online faculty, and robotics trainer before doing my PhD. I mostly work in areas of HEMT, sensors and IoT, microfabrication, and a bit of ML and AI. So the class schedule for this whole semester is Tuesday, 7 p.m. And this same meet link will be available through, like you can join this link for the class. All the recording of this class will also be available on the YouTube channel mentioned here. And in case you want to know more about me, or you have some queries or doubt, you can write to me over the email, or you can check my profile. Fine. So before starting this session, if you have any doubt relating to week one, whatever is taught, you can ask, or we can discuss even after the class. So if you have doubt, you are most welcome. And throughout the session, I'll not be able to check messages. So unmute yourself and speak if you have anything to say. Fine. Yeah. Fine. Can we proceed?
Yes, sir.
Okay. So first, we will be discussing. Yeah. First, we will be discussing some of the topics already covered in our uh, week one, like which sir have already taught. So just a brief summary of the things we that has already been covered. I will not be covering the first class since that was the overview of the uh, whole you see the course. Okay, that will be covering anyway one by one. So I'll start from the second lecture. That in fact that is the topic of the week. That is substrate, substrate and cleaning and clean room. Right. Wherever you have doubt, you can just unmute and you can ask. Fine. Wherever you are not able to understand or you want some clarification, you are most welcome to unmute and ask. Fine. So let's start with uh, a brief summary of substrate. Okay. So as we have also seen in the week one of the lecture, that a substrate is the base material on which micro and nanofabrication is performed. And what is microfabrication and what is nanofabrication? This has a bit been covered in the lecture where we talked about when our devices or whatever we are making is in the dimensions of micrometers, then we call that uh, process of fabrication as, or that skill or science of fabrication as microfabrication. Whereas when we are making some objects, some devices, circuits in the dimensions of nanometers, where at least one dimension is in nanometers, that is called as nanofabrication. And for all these processes to take place, we start with some base material, and that is known as the substrate. It is very important for integrated circuits and structure (IC), which you must be aware of, like whatever electronic devices we are using mostly have an integrated circuit inside it, or commonly called as IC. Okay. And it also have uh, big impact on the properties and applications of the outcome. So what we will make will also have will also have some properties due to the substrate. So selection of substrate or the starting material is very important. Okay, so there are some common substrate that are available for different purposes. Silicon is the first and the most preferred, most common substrate that is used in microfabrication industry throughout the world. Okay, be it Intel, be it TSMC, be it Samsung. These are some big name or Micron. Okay, these are some big names in the field of microfabrication, and these all work on silicon because the silicon technology have matured well, and we are able to get very high purity silicon. That is one of the biggest region that we are uh, working with silicon very commonly, and it can be considered as the workhorse for micro and nano fabrication. Second comes gallium arsenide. So when we are talking about silicon and germanium, these are like if you see the periodic table of elements, there is something called as metal. Are you getting me, Nitin?
Yes, sir.
Okay. You are. What is your background? Like you are from which field?
Mechanical engineering.
Mechanical engineering. Fine. Uh, BTech or you have completed BTech?
I have done masters also, but
Okay.
my specialization is thermal. But
Hmm.
I'm doing PhD in material science.
Okay, great. So are you working in something related to MEMS or like that?
I have actually learned a subject called mechatronics, where there is a portion
Okay.
in MEMS, but
Okay.
that was long back.
Okay. Not an issue. Wherever you have doubt, you can ask. Fine. So if you see the periodic table, I forgot to put the periodic table here. Okay. So if we see the periodic table, they are mostly divided into three parts. That is, uh, there are some elements that are metallic in nature, some mostly on the left hand side of the periodic table. On the right hand side, we have mostly non-metals. Okay, but in between, things like silicon and germanium, they are represented as metalloids. So they are non-metal at lower temperature, and they behave a bit conductive at higher temperatures. So this we know, silicon, and one is the germanium. Okay, the germanium in fact was the first semiconductor that was used. Okay, but now similar property has been found when we make compounds, mostly 3,5 compounds like group 3 and group 5. When we make a compound out of it, we see that there are some uh, con- uh, compounds that actually behave like a semiconductor. So these are compound semiconductor, and arsenide as well as gallium nitride are some of the common uh, compound semiconductors. Okay, gallium arsenide has found a lot of use in case of optoelectronics, LEDs, and RF application, as well as high electron mobility, uh, on which HEMTs are made. Okay, then comes sapphire. Okay, which is used for growing nitrides and nitrides. When we are talking about, we are mostly talking about the 3,5. We are 3,5 means hello. Anit, Anitras, are you saying something?
I'm sorry, sir. Nothing.
Okay, yeah,
Thank you.
fine. So when we are talking about nitrates, so 3,5 compounds, nitrogen falls in the group 5 of the periodic table, and gallium nitride, indium nitride, aluminum nitride, these are actually uh, compound semiconductors, and they are grown over sapphire. Okay, and since sapphire is a very tolerant material, like tolerates a lot of temperature, like it can resist a lot of temperature, and chemically very inert, in, as well as it has some good optical properties, like it is transparent. Okay, so it is used to grow nitrides and some optoelectronic devices like GaN, gallium nitride. Okay, and a very hard material. Okay, so one we have seen is silicon, third is gallium arsenide, third, these are substrate we are talking about. Okay, then sapphire, then comes germanium. Okay, this was one of the first semiconductors used for transistors, but it had some demerits, like it was not very well working, not working very well when we go for higher temperature, not very resistant. That is why it was, it is not that popular nowadays, but still it has found some application like 359 materials. Epitaxy is something where we grow crystals according to, like we grow these materials as aligned with the substrate crystal. Okay, in that case, germanium is used. Then comes silicon carbide, which is a very hard material, uh, having hardness comparable to diamond. It is generally used in high temperature application and as substrate for for gallium nitride. GaN, I was saying. Okay, gallium nitride, I'm referring as GaN. Then quartz and glass are also used specifically in case of uh, RF application photomask. We will learn about lithography in subsequent lectures. There we will see something called as photomask. They are made up of glass and quartz. And sometimes we have to work with microfluids, like fluids flowing in uh, microliters, you can say. Okay, so these are called microfluidics. They are also made using quartz and glass, such MEMS structure. Then plastic like Krafton, PET. Okay, these are flexible, low cost, and limited to very low temperature resistant. Like they will burn at a bit higher temperature. So for low temperature application, and nowadays flexible electronics is also growing. So these are some substrate that we encounter, and whatever we will learn, we will mostly you will mostly see that most of the common things are being made over silicon. Okay, silicon is the workhorse for micro and nano fabrication. Even sometimes we are working with gallium nitride or gallium arsenide that is actually grown over silicon. So the substrate is ideally silicon only, and some layer of gallium arsenide or gallium nitride or aluminum gallium nitride has been grown over it. Okay, so we will be discussing more in general about silicon. Okay, so how this wafer, when I showed this wafer. Okay, wafer means a thin, very thin, you can say a very thin slice. Okay, so how this wafer of this substrate, silicon substrate, is being made. So it is made from the starting material called as polysilicon. Polysilicon means silicon having different crystal orientation that has already been purified. So we start with 5,9 purity, that is 99.999% purity. And but the problem with this is that this is polysilicon, like the crystal is not all oriented. Okay, so there is a method called as Cholesky method or CZ method, in which this polysilicon is melted. If some dopants are to be added, uh, do everyone knows what is a dopant? Can anyone tell me what is a dopant? Hello, yeah.
Uh, so dopant is a material
Hmm.
which is added to the semiconductor in order to make it a conductive material.
So then will it not become like become metallic? So why don't we use metal instead?
Uh, uh, So basically, we are making a semiconductor which is enriched with either holes or electrons.
Mhm. See, we are you are in right direction, but you went a bit ahead. Okay,
Ah,
we are not making it fully conductive, but we are
ah,
increasing the conductivity of it. So it is, you are telling it very correctly, but just it
mm,
is the play of words. Okay,
okay,
so
okay,
some materials which enhance the conductivity, so that we can control it better, like in a better way. Okay, so this whole polysilicon is melted, then dopants are added, and then seed crystal. Since this whole thing we want in a single crystal, the whole wafer we want to be a single crystal, like there should be no breakage of crystal structure. Okay, so atom by atom, like there should be no break. uh, for that we are inserting the seed crystal, so we are putting a starting crystal that will determine the orientation of the whole thing we are making. Okay, so a seed crystal is, and the molten thing that will uh, then we will just rotate and pull it out. So the silicon atoms will try to align them to the crystal, and it, when we will take it out, it will be in the same orientation as the seed crystal. So this is something very important. Then when we are whatever seed crystal we are putting, the orientation of the uh, whole wafers that is coming will depend on this. So rotate and pull. This is the CZ method, and that is one of the most common methods used in fabrication of the wafer. Okay. Then the whole a cylindrical thing is obtained, as you can see here, and this is called as ingot. Okay, it big cylinder nowadays. This cylinder is in thickness of like going beyond your height and all, 5 6 feet. Earlier it used to be very small. So earlier we used to get very small, uh, what you say, very small wafers. Nowadays the wafers that we are getting can be as big as 12 inches or 18 inches. Okay, but earlier it was uh, 1 inch, 2 inch, 3 inch. Still 3 4 inch are very common wafers for lab purpose, but in industrial purpose they have now shifted towards 12-inch and 18-inch wafers. Okay, so this ingot is then cut with a saw, kind of diamond saw. Okay, then it is grinded, like it is smoothened out, flattened. And why this flattening is done, I will show you in a subsequent slide. Okay, then uh, polishing. It is polished. It is mirror, like you will see it as a mirror finish structure. Okay, uh, those have you all seen a silicon wafer, Nitin? I think you must have seen, right? Hello, you have seen or not? I was unable to hear you.
No, sir, no.
No, okay. Uh, Anyone else who have seen a silicon wafer or handled a silicon wafer? Okay, so okay, in some class, I think I don't have a silicon wafer here. So in some class, I will show you how what a silicon wafer looks like. Okay, it is like very, very mirror finish kind of structure. Okay, according to application, you can have one side polished or both side polished. This polishing is nothing like polished. It is uh, like it is so the surface is made so smooth that it becomes like a mirror. Okay, very smooth. And In general application, we have one side polished, but when we go for high MEMS and these things, both side polished wafers are also used. But for most of the application that I have mostly encountered, or general applications, you will see that one side polish is there. Okay. Now there was some orientation flat was being done. Okay. So as I was talking about, what are the wafer specification and how they will look like. Okay, they range from 1 inch to, oh, sorry, I was telling 18 inch, right? So 12 inch, that is most of the standard in industry PC. Okay, 12, even 14 inch. Okay, this is the diameter we are talking about. Okay, 1 inch, 2 inch, these are diameter of the wafer. That is, if we consider this as the wafer, this. Okay, so they range from 1 inch to 14 inch. And as the size increases, the thickness of these wafers will also increase. Generally, for 1 inch, we get something around 100 to 150 micrometers thickness. Okay, that will increase. Like for in general, in our lab, like we use 3-inch wafers, those are around 350 microns thick. Okay, and some 8-inch wafer also I have, that is uh, around 900 micron thick. Okay, so you can understand that as the thickness will grow, as the size will be larger, we will get thicker wafers because it will break if it is very thin. Okay, then uh, the wafers are identified according to their crystallographic orientation, 100, 111. Are you aware of this crystallographic orientation, what it is? Yes, anyone? I think, yeah, Shaumya, are you there? Kethavat, hello. Yes, anyone? Uh, Please unmute yourself and speak because I will not be able to check the messages. Hello, Kethavat. Okay. Yeah, the question is, do you know about this crystallographic orientation, like 100, 111? And okay. Yes, anyone else would like to add? Nitin, Anitaraz, or Soumya Mudler?
So are they related to the crystal structure of NPTEL?
Yes. So these are related to the crystal structure. Since you are from metal, like you are working in metallurgy, you must be aware of this crystal structure or crystallography, right? So this, as I was talking about, we want the whole wafer to be of one single crystal. Okay, so if it is of one single crystal, when it is cut as a wafer, the top plane will have some orientation. Okay, and if you are not aware of anyone if is not aware of crystallographic orientation, just search something on the YouTube. You will find some basic uh, Miller in there. And if you are not able to understand, we can discuss in any class once these questions are over and all. Right? So they are oriented at the top plane is oriented in one single crystal structure. Okay, so they will be available as 100, 111, or 110 structure. Mostly 100 and 111 are the common one. Then p type and n type, we talked about dopant. So how will you identify whether it is a p-type, n-type? Just by seeing the wafer. Okay, the wafer will be circular, but if it has one single cut, okay, or notch. Nowadays when we are going for bigger wafer, like cutting it through is a like wastage of material. Okay, but for a smaller one you will find these cuts. Okay, big primary cut and secondary. Big cut is primary, small cut is secondary. So if it is circular and one big single cut, that is a p-type 111 wafer. If it is having one cut and a small cut at around 45 degrees, okay, this is n-type 111. If we have a cut, a primary cut and a secondary cut at 180-degree angle, then it is a n-type 100, having 100 plane crystal plane on the top. And if we have the one with 90-degree, like the angle between them is 90-degree, then it is a p-type 100. Fine till here? Any confusion? Then there are some grades. When you go to buy these wafers, you will find some grade. We are mostly using for microfabrication, we are using prime grade silicon. That is the best quality of wafer. Okay. Then comes solar grade. So you see that in case of solar cells, some uh, like some breakage in the crystal will also work fine. It is okay. Okay. The cost will be lesser compared to this prime grade, and there will be some breakage. So it is fine. So this second is solar grade, then is test grade or mechanical grade. Okay. So there are three type of wafers. So if you are first starting in this field or you are learning in this field, you should know where to start with. You should start with prime grade wafer, and as per your need, you will take the thickness. And if your the work you are going to do is anything related to one plane structure, then you will choose accordingly. Otherwise, go for the cheapest one. Okay, uh, whichever you are getting, and then p type and type you will have to decide. Then they are fabricated. We have seen the CZ method, and then there is float zone method also. That is not commonly used. It is more relevant in case of germanium. Okay, thickness will depend on application and the size. Okay, resistivity will certainly depend on the doping level. Ranges from very highly doped to insulating. If it is almost nothing is doped, but you will rarely find intrinsic silicon. Okay, it is having some small doping. Okay, so resistivity will depend on that. According to your use, you can take a single side polished or double side polished. Anything till here? Any questions? Hello, hello. Am I audible? Yes. Are you able to hear me?
Yes, sir. Yes.
Okay, fine. Please, like this is a interactive session. Okay, so you also are. Everyone is expected to speak. Okay, so be ready to speak up. I might be asking questions as well as you are free to ask by unmuting yourself. Okay, then there is something called as zone refining. Like we have this whole, this is mostly relevant in case of germanium. It is generally done. Okay, we have seen that in case of silicon, it is generally made using CZ method. In in case of germanium and some other semiconductors, zone refining is used. So what it is done is that we have a rod kind of structure. It is melted and this melting part is moved forward. Okay. So the concept is that the solid form during crystal growth is purer than the starting melt. Okay. So it is such that when we are taking out the solid out of this melt, the impurity will try to remain in the melt. Okay. Like when the melt impurities will try to move along with the molten part and the solid will get purer and purer. This is done multiple times. Okay. Generally, in this case, something called as binary phase diagrams are used to understand. Let's not go very deep, otherwise, in the first class itself, it will become too boring. Okay. We will mostly be discussing about fabrication part. Okay. So, different impurities, just this is an overview. Okay. That different impurities have different K value, that is the distribution coefficient, and according to that, they tend to be in the molten part or towards the pure crystal part. Okay, there are some low values, low K things like iron and gold, and there are some high K things like the dopant. Okay, low K means they will be easy to remove. Okay, high K means they are difficult to remove, like the dopants. Okay, that is why you see that when we are cleaning, the dopants will not come out very quick, easily, although they are also an impurity. Doping itself means impurity. Crystal growth method, we have seen CZ method. Okay, but with the CZ method, there is a problem that when you are trying to make the same thing, use the same method for gallium arsenide, arsenic evaporates. Okay, when it is molten state, right? So arsenic will evaporate, and so you will have to add some capping agent, and then if you are doing this thermal management, like you are not going too high, then you will get an irregular sept in God, that cylindrical part. Okay, so we go for the float zone method that we I talked about, that where we are using the heated melt to like heating coils to melt the portion and then move forward. So this will actually that molten part will actually carry the impurities and move forward. You as it moves forward, this area will cool and the molten part will carry the impurities with it. And this is done multiple times so that we can get a very pure or ultra pure material. Fine. Then there is something called as gradient freeze or Bridgman Stockbarger method. Okay. Yeah. I think it is not showing the. Are you seeing the gradient freeze method slide? Yeah.
Yes, sir.
Okay. So in this case, a sealed ampule with melt, like molten part of the material, is lowered in a temperature gradient furnace. So different temperatures are maintained. A furnace with different temperature. So at the bottom part, which is a bit colder, you can say, the crystallization will start. But so this has the advantage that it has lower dislocation density compared to CZ method and generally preferred for high quality gallium arsenide wafers. So we have seen three methods, right? CZ, FZ, and Bridgman Stockbarger. Each method have different advantage and different challenges. According to the material we use, we will be using that method. Fine. Like we saw that CZ is used for silicon, Bridgman-Stockbarger is used in case of gallium arsenide. FZ method or float zone method is mostly used for germanium. So this is for making it ultra pure. Actually, the starting material itself is quite pure, and we are going for very pure, 5969 purities, like that. Why? Because if it is impure, it will have some effect on our uh, wafer that we are starting with. Okay, any if we concentrate on silicon itself, the atomic density is generally 10 to the power 22 atoms per centimeter cube. Impurities added are in the range of 10 to the power 14 to 10 to the power 12 atoms per centimeter cube. In general, if you find any questions, it is generally taken as 10 to the power 15 atoms per centimeter cube. See that these are not in SI unit, because most of the things that are being talked here, they are the standards used in the fab, like in general Intel fab and this, and they are located in USA. So some of the standards you will find will differ from the SI unit. Okay, they are generally, you see, 1 2 3 4 5 6 7 8. So this is known as 8-9 purity. There is 99.99999% purity, that is 10 ppb, 10 parts per billion impurity. That is the purity level of the silicon wafer we are generally getting. The common growth method is CZ. Float zone silicon is also made, but where we want very high purity compared to the general. Okay, there is something called a vertical gradient method or Bridgman method, that gives us moderate purity, but in case of gallium arsenide, that is the preferred method. Okay, then whatever we are getting, we are grinding. I have shown it earlier also. We are grinding, polishing, okay, and then cuts are put to make the wafer that we get. The final wafer that we get will be prime prime grade. So if you see that this whole when we are talking about FZ method or CZ method, the whole ingot will not be very pure. There will be difference in purity. Okay, so this difference in purity gives us different grade of silicon wafer. One is prime grade, then yeah, the prime grade, that is if we see this ingot, that is a cylindrical shape. So one end will be the purest one, the other end will be the impurest one if we compare in between. So from the purest part, we get the prime grade wafer. From the impurest part, we get the test grade or the mechanical grade wafer. And in between, we get the solar grade wafer. And depending on the application, we will take 100, 111, or 110 planes. Then polishing single side, double side. When we are talking about wafers, we are talking about single crystal, very high purity used in electronics, and as well as microfabrication, what we are talking about. Okay, microfabrication and nanofabrication, they are generally used in case of electronic material like chip, like uh, this processor and these things. Okay, for low quality cheap things like we say China made things, right? It will be a multi-crystalline thing. Okay, then after you have selected the wafer. We have talked a lot about this wafer thing, right? After we have selected the wafer, what are the next steps? Next is this whole process is to be very, very clean. In one of the class, we will be discussing that what is the significance of purity, okay? Cleanliness. This has to be very clean, okay? Because we have to go for very high quality application, and these materials, these structures that we are talking about, they are in micro and nanometer range, and the dust and other things that we encounter are also in the same range. So even one dust particle can have effect on them, okay? That is why this next thing that is very important is the cleaning of these wafers, okay? So to clean this, first thing is that you have to be in a clean environment. Till here, any questions? Hello. Yes, any questions? I think, yeah. Soumya, Mudlayer, are you there? Hello. You are not audible. Okay. Any questions? You can ask in. Okay. So, clean room is the place where we will start this whole process. So, first thing is that we want to clean it, and to clean it, it cannot be done in a unclean environment. So, we go for something called as clean room. Okay. It is very essential to maintain purity during micro and nanofabrication. The second thing is that there can be some contaminants, and that can impact the device yield and reliability, and that is why we are going for clean room. There are some standards which you must have seen in the classroom, or if you want, I will also put that there are different class of clean rooms. Okay, class 1, class 10, like 1 is the purest one, class 10 is a bit impure, class 100, class 1000, like that. In India, I think ISC have class 100 clean room, and that also some part of it. Class 1000 is there in some labs to like 3 4 facilities throughout India, and 10,000 and these things are there. Class 100 is in there in Siri Pilani also. Like there are very limited good clean rooms in India where you can work very high quality clean room. Some standard clean room are even there in case of pharma companies. They also use clean room for their purpose. Okay, so what you have to take care is that in this whole process you have to take care that no dust, no pollen, no smoke, no bacteria. Yes. Is my screen visible again?
Yes, sir.
Okay, so why we are concerned, like what are the pollutants or contaminants we are concerned about? These are dust, pollen, smoke, bacteria, atmospheric pollutants, human origin oils like we generally apply on our head and all, sweat, and some chemical impurities. So we have to be very like we have to be free from these. Okay, for this like to be in this environment. So there is an example is that Intel and Micron, they have clean rooms. Okay, so how this is done is that there are some pressurized plenums that are used that pushes the filtered air into the clean room. So this The air that we get in the clean room, that is a bit pressurized. What and that is clean air, but it is a bit pressurized. That will ensure that sorry, if you are in a room that is having high pressure, okay, this one is having high pressure compared to the atmospheric pressure. So what will happen? Can anyone tell? If a door is opened or a window is opened for a short duration here, what will happen if yes,
It will
Anu.
contaminate the rooms.
But what we have done is that we have put
Ah,
higher pressure, a pressure higher than this atmospheric pressure inside the room.
okay.
So what will
So
happen
the
in this
pressure
case?
pressure will get decreased, sir.
Decrease. A-
Ah,
and how will that happen?
because we are maintaining a very high pressure, so outside environment is lower, so the window is open, so the pressure gets reduced. The
That
air
is
from the room gets escaped throughout the window,
yes. So
so the
air
pressure is decreased.
yes. So that is the thing that the air will get out from the window. Okay.
Oh, yeah.
There is no chance that something will get in the inside. Okay, the airflow should always be from the clean room to outside, never from outside to clean room if some opening is there. Fine. If something and for that we use a pressurized planner. That means we have a higher pressure inside the room so that if by mistake some opening is there, the air from inside will come out, but outside air will not go in because there can be some unclean things from uh, in outside air that we don't want in. Okay, so this is the first thing that is done. Second is HEPA filters. These are very high efficiency filters, HEPA, and sometimes HEGA filters are also used. They are even better than HEPA filters. Okay, they ensure high quality air filtration. So the normal air filters we use in case of our home, like this in ACs and all, those are not used. In case of clean room, some special quality of filters called as HEPA filters are used. And then inside, there always is a laminar airflow. That means a airflow from the bottom of the clean room to the top. There is always a flow of air, and that is laminar. Like if anything falls, it will just like it will take that particle or dust anything with it, and it will go out to be cleaned. Okay. Then the second thing is that there are different zones in the clean room. So when you enter, you will be entering like you will actually contain some contaminants. So you will be like you will be aired properly, like good pressure of air will be flown over you so that anything like on you will be removed. You will be wearing some apron and these things. Then you are entering an area that is the main clean room. Then there are something where it is clean, but it is not that very clean. And where you are actually working, that is a subfab or a very even cleaner than that. So there are different zones of clean room. Generally, zone 1, zone 2, zone 3, and zone 4 are used. Okay. To maintain such clean rooms, it is very costly. A typical fab needs around $10 billion. We are not talking in 10 cents of rupees. Okay, $10 billion of investment to start a small fab. Okay, and that might be the reason that there are a very few fab throughout the world. Forget about India. Okay, in India, we don't have a commercial fab facility yet, though uh, the government is investing a lot, and we have some test facility like lab kind of facilities. And in some years, you will find that India will also have some commercial facility. Okay, so we have seen that yes. So when we are talking about clean room, first and foremost problem is human. We ourselves are the problem of clean room. That we have hair, we have skin falling, and different things. Okay, so atmosphere, like in the atmosphere itself, there are different things. In the equipments we use, there it can have some dust particle and all. Chemical impurities can be there, metal can be there. Okay, so what is the effect of this? That if we are talking about MOSFET, like suppose we are going to make a transistor or MOSFET or a RAM, their operation can be affected by these small things. Okay, so the thing is that we have to be in a clean environment called as clean room. Then we start with cleaning. And whenever we are talking about cleaning, what is the first thing that we talk about for cleaning is the is the water. Okay, most of the cleaning in our household we are doing with water, right? So here the water itself has to be very clean. Okay, very pure, even purer than the distilled water, and even free of ions. And how do we make it? That we are testing the uh, conductivity. If we have to remove all the ions, first it is obviously distilled, and then it is continuously looped through the polishing loop, that is cleaning it and degrading it, like removing all the ions and all. So particle filtration is done, water softening is done, activated carbon filters are used, RO, reverse osmosis is used, then electro deionization. This is the part which reduces the ion content. Then resin based polishing is done to ensure this value 18.2 mega ohms centimeter. Mega ohms centimeter, that means the uh, current flow through this water will be very less, almost negligible. Okay, and that is this kind of water is known as deionized water. Or
So your voice is not audible. It's
yeah.
breaking.
Okay, hello, is it audible
So
now?
your
Yeah,
voice
just
is breaking.
okay, just a minute, let me try. Is it better now?
So now it is okay.
Yeah. Okay. uh,
Thank you.
is my screen visible?
Yes, sir.
Okay, but it is not visible on my own screen. I don't know why.
Okay.
Yes. Yeah, now it's visible. And am I audible clearly now?
Yes, sir.
Okay, fine. Sorry, I don't know. Like today, I started the class, and this like Wi-Fi and everything got disconnected. What happened? I don't know. Okay, so we are maintaining till where you were able to hear me. Hello.
We were talking about clean room.
Okay. After clean room. The
And the
next
use
thing,
of water, like distilled
yeah,
water.
okay. So mostly we are uh, most of the things that I had was talking was audible then. Okay, so we are maintaining a very low iron content, and we are trying to get close to this 18.2 mega ohm centimeter. This is very high resistance, resistivity of the water. That means no current should ideally flow through this water. Okay, no ions, no current. Fine. And this water is known as deionized water or DI water. It is even purer than distilled water. Okay. The chemicals that we are using, they are also very pure. They are called as ultra pure chemicals, very much costlier than the normal lab chemicals that you use. Okay. They are called as CMOS grade or semiconductor grade. Okay. Ve- uh, very pure quality. Over contamination level is below, like you say, it is in the range of 100 to 200 ppb, parts per billion. So that is very, very pure. Particle density, this is actually itself covered in case of this clean room, but the chemical that we get there also, the particle is to be very clean. Okay, like you see HPLC grade or ACS pure grade chemicals. These itself, ACS pure if you search, ACS is American Chemical Society, right? So the chemistry people, the purity that they maintain, they are also not clean enough for us when we are going for semiconductor fabrication or microfabrication or nanofabrication. So even purer than that. Okay, so it is recommended. So what to do in a clean room is that use CMOS grade chemicals for highest purity. The uh, the dust particle should be very, very minimal. In fact, if you are in a clean room, the dust particle size itself is like controlled. Contamination level is of should be in, like, this is the highest limit, right? It should be in parts per trillion, not even parts per billion. Okay, the gases that we use, nitrogen, oxygen, or whatever gas you are using for your experiment or your work, that also should be 59 to 69 purity. 59 means 99.999. Okay, 69 means 99.999 Okay, so to ensure this, we cannot have a gas cylinder transported from far away. So that also have to be generated on site for maximum purity with very good inline purifier. And these are very important for processes like chemical vapor deposition that we will be studying in deposition chapter. That is, I think, third unit. Okay, these you can go through. I will be anyway sharing these ones. Any confusion till here? Anyone? Okay. So overall, you go through all these policies. What are the requirements? Okay. Then we are coming to something which is an important part of our lecture, that is wafer cleaning. We are in a clean room. We have very good chemicals. We are wearing clothes which don't expose anything out. Okay, we are using good water. We are using good chemical. Good water means what is the quality of water that we are using? Anyone? What is it called? The water that we use in the fab? Yes, I just told some slides back, I think. Hello. Am I audible?
Yes, sir.
Yeah, so can you tell me the water that we are using here? That is the DI water, deionized water. Okay. The chemicals that we are using, that is CMOS grade chemical. Okay. Then everything is there. Then what we are going to do is that we are going to clean the wafer that we got. Okay. Fun, the main purpose is to remove any particle or chemical contaminants from the wafer. Okay. Very important for any critical step so that we get very high, we get good quality of devices that we make. Our focus primarily is on silicon wafer, and a similar thing can also be done during the for other wafers. Okay, if you are doing the wafer cleaning well and in a clean environment, your chances of getting good devices increases a lot. Okay, if you don't have a good clean room or you are not doing cleaning properly, uh, the output will suffer. The output percentage will decrease drastically. Okay, so there are some basic cleans like Piranha clean, that is the most common one, where a uh, mixture of hydrogen peroxide and sulfuric acid, both are very high oxidizing agent. Okay, these are used for removing organics, photoresist, and making it ready for the next step of cleaning. Okay, so this is the basic. It was actually developed for this cleaning utensils first, steel utensils and all, which were very unclean. It was actually made for that, but later it was found that it have application here also, so it was good. And it acts like the piranha fish, which like which are very small in size but can are carnivorous, and they can eat human itself in like 10 to 20 minutes. Okay.
Sir, excuse me, are you presenting slide number 18?
No, I am presenting 21, slide 21.
Sir, it's the slide is stuck actually. It's still showing
Okay.
18. Slide 18.
Yeah, everyone is seeing the slide 18, Anitras and Soumya.
So 21, piranha
21.
cleaning.
Okay, so I think it might be the network issue from your side, Nitin.
Okay, sir.
Yeah. Anyway, I will be sharing this whole slides. Okay, and you will see the video also. Fine. Uh, Try refreshing your network. It might correct the problem. Okay.
Okay, sir.
So this piranha fish, like they are very small in size and they are carnivorous and they can eat the whole human itself in some fraction of minutes or something. Okay, and based on that, it is the name because here also it like the chemical is very vibrant and like it will eat out all the organic things present there. Okay, this H2SO4 and H2O2 in the ratio of 4 is to 1 is mixed. Okay, and temperature of 80 to 120 degrees Celsius is there. The mixture itself, when you mix, it is boiling and it is hot. Okay, so you don't have to heat separately. It itself is very like it is very hot. So you don't keep these things mixed. You mix and then you do this. Okay, and that also very like it is a very vibrant reaction. Okay, oxidation, uh, like it oxidizes everything to carbon, which is then converted to CO2 and it flies away. Okay, very exothermic and very dangerous. So you have to be very cautious. Always use PP and different protective things before doing this thing. Then comes something called as RCA clean or SC1 clean, uh, RCA clean or SC clean, or this is the RCA means it was developed in Radio Corporation of America. It was developed in Radio Corporation of America. That is why the name RCA, but nowadays most commonly called as SC or standard cleaning. Okay, it has two parts, SC1 and SC2. Okay, it was developed by Warner Kern in 1960, working in Radio Corporation of America. And this is one of the standards for wafer cleaning. Though there are different methods, like everyone can use as per their wish, but this is something that is very standard. SC1 is used for removing organic part, whatever is left from piranha, and other particle. SC2 is used for removing metals, and then metal or metal ions, you can say. Then there is an optional HF dip to remove oxide. Why? I will tell you later. Okay. RCA1 or SC1, or also called as APM, because it has a combination of ammonia peroxide. Okay, hydrogen peroxide. So APM means ammonia peroxide mixture. They are mixed in different ratios. A temperature of 40 to 80 degree Celsius is used, and these wafers are dipped into it. It oxidizes metals, forms soluble complex, and remove particles. But it actually produces some ammonia complexes which are harmful for us. So never inhale. It has to be done in the fume hood, where these gases are exhausted and treated and then sent outside. Okay. Then is SC2 or standard cleaning 2 or RCA2, where HCl and peroxide, hydrogen peroxide mixture. So HPM, it is HCl and peroxide mixture. Okay. They are taken in the ratio of 1 is to 1 is to 6 and or 1 is to 2 is to 8. Okay. Here also it oxidizes metals and forms soluble chlorides. Since it is HCl, and you must have studied in your not undergraduate, in your intermediate chemistry and all, that acids actually react with metals and like release hydrogen gas and make some other complexes. Okay, so this is used to remove this. But in this process, what happens is that a thin layer of silicon dioxide is formed on the top. It removes everything, and a very thin layer of native oxide or silicon is there. Silicon dioxide, SiO2, is formed on the top layer. To remove that, sometimes, like not sometimes, mostly what we do is that for cleaning, well, we put it inside a HF, hydrofluoric acid, which is actually very dangerous chemical again. One is to like 1 is to 100 ratio of HF to H2O, to 1 is to 50 ratio. Okay, 1 to 2 minutes at room temperature is kept. Okay, it will remove the SiO2 and leave a pure silicon on the top. And to identify it, like when I started working in this field, what happened is that I used to keep it and was not able to understand how, like, how we know that it is getting clean, because that is in nanometers thickness. You will not be able to see it with your naked eyes. So the best test is that oxide is hydrophilic. That means if you dip it in water, it will actually, water will remain on it. Once this native oxide is removed, it will become very hydrophobic, because silicon is hydrophobic in nature. So once it is done, you dip in pure DI water and you take out, nothing will remain on it. That means it is cleaned. Okay, so it removes, and from here we have like earlier we made a very clean wafer. We chose the best wafer. We started working in a clean environment. Now we have cleaned the wafer surface, because most of the work is to be done on the top surface of the wafer. Okay, but very make sure that this is highly dangerous. It is so dangerous that it even uh, like goes through the bones, it is said, and you will not even feel it, that it has corroded your bone or went through the bone. So very cautious. It Teflon gloves are used. Normal gloves will not work here. Teflon gloves are used to handle such materials. Okay, lab yeah, the tweezers, everything is to be of very good quality. Very sorry. Yeah, we are. We also have to take care that what chemical will go in what kind of beaker. Okay, like quast or glass beakers are used for normal chemicals, but when we are talking about acid or HF and these things, we go with Teflon beakers because they don't react with Teflon. That is a plastic-like thing, but uh, very very stable and it is not disturbed. Pyrex or soda lime glass is not used because it has contamination, as well as if you are putting acid or something in it, it will crack and everything will spill out. The tweezer that we use, I think I have one tweezer here. Are you able to see my video?
Yes, sir.
Yeah. So, like though these tweezers, they look very similar to the tweezers that you might be aware of, but they are of very good quality, as well as they have some property like they are coated with Teflon. So there is a Teflon coating, okay, or like this one is for general purpose handling. It is actually not wafer handling. The wafer one will have at the last a Teflon Teflon part that is for handling that. This is for handling small small bits of some wafer if it has broken or something. Okay, because metal tweezers or colored or painted things are not allowed. Okay, in all the steps, whatever you have seen, there is one very important thing, that is rinsing and drying. So whatever step you are doing, after that you have to put it in DI water, the wafer or anything, because water is the actual cleaning agent you will can see. Okay, and then it is dried by using very pure quality of nitrogen to dry it, to remove the water that is sticking over it. Okay, rinse 3 to 5 times, then nitrogen gun to spin dry to prevent any stains, no marking. Okay, always you have to wear PP kits. Okay, like everything covered, even nose, everything covered. Wafer, like it is big, you don't have to handle it from the center. Use the sides, because whenever you are handling it, actually it is making some markings over it, and that is uh, going to create some problems in the future. Okay, and minimize minimize the contact of your devices, your wafer, with anything, including yourself. That will ensure that you are making good quality, giving good quality output. Okay, now let's discuss some questions related to this, uh, whatever we have discussed till now. Okay, any questions till here? Anything in your mind which you are not able to understand, you are free to ask. You can even post in the message if you are not able to unmute, speak up. I will be checking the messages. Okay, if no questions, can we move forward?
Yes, sir.
Yeah, okay. So let's start, and I am expecting you people to answer. Okay, let's start with problem one. That is, how are silicon wafers produced from ingot? from CZ method, that is Solarsky method, float gen, float gen zone method, CZ method, both or none of the above. Yes,
Both the methods.
both the methods. And which one will give a better yield, CZ or FZ?
Um,
Which, yeah, yeah, please speak.
CG.
CZ will give better yield, and which one will give better quality, purity,
Uh, Purity. CZ will give less purity. So float zone will give high purities.
high purity, but CZ is faster process, you can say. So it will give
Okay.
better yield. Okay. So let's come to
So
second question.
CZ is better, sir.
Yeah.
So CZ.
Yeah.
Okay.
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 So next question, that is problem two. What is the resistivity of the deionized water? 17.8 milliohm. Is the slide visible? Problem two.
No, sir. Ah,
Huh?
yes. Now it is visible.
Okay. There is some delay. Yeah, what is the resistivity of the deionized water? 17.8 milliohm centimeter, 18.6 mega ohm, 20.1 mega ohm centimeter, or 18.6 milliohm centimeter? Yes,
Sir, B option.
B option. Yes, very good. Okay, so this is something we have covered, right? And why do we need such high purity, high resistivity? Yes, anyone? Okay, so let's move to our next question. Which of the following are allowed processes in the clean room as per the contamination policy? Sir also talked about contamination policy. I also talked about okay, and I have put in the slides also, but we didn't discuss that in much details. Okay, so if you have attended the lecture, you must be there. Okay, so aluminum contact deposited on silicon can go to RCA clean in level 2 wet bench. Is this allowed? Yes, anyone? Yes, anyone would like to answer that? Is the first one allowed? Yes, Anita. Anita Raz, right? Yeah,
It is not allowed, sir.
it is not allowed. Why?
In RCA cleaning, I think we use a very highly acidic agent.
Huh,
So in RCA cleaning, it is not allowed.
okay. And level 2 wet bench. Okay, fine. Next is removal of photoresist of pattern sample from lithography in level 1 wet bench. We have done some lithography process that, okay, and then we have to like we have not studied lithography yet, but let's say that we have to remove some organic materials from there, and this is generally done in acetone. Okay, and this is to be done in level 1 wet bench. Is it allowed? Are you understanding these levels? Level 1, level 2, level 3? Yes, anyone would like to answer which of these are allowed? Yes, Anyone? Okay. Uh, yes, if you are not very clear about these levels of clean room, we will revise this in the next class also, not an issue. Okay. These are like there is certain rule that from which level generally from a cleaner part you can go to a bit lower quality part, but from a lower quality part you cannot go directly to a clean very clean part. Okay, it has to undergo some processes. Okay, so in this case you can see that a tungsten contact deposited on silicon can go to a RC cleaner level 3. Okay, whereas aluminum contact deposited on silicon cannot go to level 2 wet bench directly, because this deposition and these things are generally done in level 3 area. Okay, and samples processed outside a clean room cannot go to level 3 wet bench. It will need to first go to level 4 where it will be cleaned and all, and it will be made compatible with level 3. I said that there are different zones, like this is level 1, level 2, level 3, level 4. Okay, so the thing is that this is the purest area, level 1. Level 2 is the a bit less clean area. Level 3 even lesser level, because you cannot maintain direct very clean area. You will have to transition. Okay, so outside we try to make clean, and then inside it we make even cleaner environment, even cleaner like that. Okay, and if you have to ensure that this is not disturbed, the moment of things can go like this. From a very clean area you can take something out to a bit unclean area, but you cannot go reverse. From an unclean area you cannot go directly to a cleaner than that area, because that will actually carry contaminants with it. Fine. Okay, now let's come to next question, that is, in what ratio are H2SO4 and H2O2 mixed for piranha cleaning? Is it 4:1, 3:2, 2:3, or 1:4? Yes, anyone? Nitin?
So for me, the slide is at some network issue, I think.
Okay. Seem to be. Yes. Anyone else? Anitraj or Soumya? Yes.
Sir, 4:1.
4:1. That is the ratio we use in case of a piranha cleaning. Okay. What is the role of H2SO4 in piranha cleaning? It oxidizes carbon to carbon dioxide. It removes metal contaminants. It removes inorganic contaminants or removes organic contaminants. Is there a delay in everyone's computer, or just some people are experiencing the delay? Are you, Anita or Soumya, are you also seeing the slides with some delay?
A little bit delay, sir.
Little bit delay. Okay. Okay. That might be due to this power cut or something that happened, right? Mm, is this- Now the internet is fine, but yet I don't know why it is behaving like this. Maybe in the next class this will be solved. It might be the problem with internet connectivity at my end. Okay, so let's answer this question. What is the role of H2SO4 in piranha cleaning? Yes, anyone? This is visible now, right? Problem 5.
So option D, to remove
Option
organic contaminants.
yes. So we are putting it in H2SO4 to remove the organic contaminants so that for the next step we are ready with without any without much of organic contaminants. Those which are hard to remove by piranha cleaning are cleaned by this RCA1. Okay. Then problem 6, that is RCA1 is used for removing or RCA1 area. Yeah, it should be just this. Okay. RCA1 removes organic contaminants, removes metal contaminants, removes inorganic contaminants, or removes chemical oxide. Yes, anyone? Yes. It also removes organic contaminants but which were not removed by the piranha. Fine. Okay. Let's move to problem 7. That is RCA2 removes metal contaminants, or here we are talking about RCA2. Okay. Metal contaminants, organic contaminants, inorganic contaminants, or chemical oxide. Yes, I think this we have discussed just now. So you should be able to answer.
So
Anyone?
option,
Y-
option
Option? Yes. Nitin, your voice was not clear. Yeah, can you repeat again?
so option A.
A. Okay. Yes, Anita Ras, you are also saying something.
So still the slide is in the previous one.
Previous one, which slide number you are seeing?
37.
Yeah, that is the slide we are talking about.
Okay, okay.
It is about RCA2. It looks similar to the previous slide. There it was RCA1. This is RCA2. Yeah. So Nitin has answered metal contaminants. Anyone would like to differ, like say, no, this is not the correct answer. Okay. So RCA2 is to remove the metal contaminants. Then comes what is the role of HF? Okay. Like we saw Piranha, RCA1, RCA2, then HF was done, right? So HF is used to remove metal contaminants, organic contaminants, inorganic contaminants, or silicon oxide. Yes. Anyone? Mm, yeah. Can I ask? Yeah, Shaumya, are you there?
Sir, D option, I think.
D option. Great. Okay. Please speak up. Don't the whole when you see the mail, you see it is written as live interactive session, right? So this is for interaction. This is to discuss. Fine. You should speak as well as give your ideas, or you can say no. Even I can be wrong, right? So you should discuss and say these things. So it is removes silicon oxide. Fine. Yeah. Now, which gloves are used to handle HF? F, Teflon gloves. Yeah, yes, Anita.
D, sir. Teflon gloves.
Teflon gloves. Yes. Teflon gloves are used to handle HF, as well as F Teflon gloves are used. That is a variation of Teflon gloves. It has some extra materials in it, right? HF is handled in Pyrex beaker, polypropylene beaker, glass beaker, or Teflon beaker. Still, I think, yeah, there's some. Yes, HF is handled in which of these? Pyrex beaker, polypropylene beaker, glass beaker, or Teflon beaker?
So B option.
B option. B or D?
Polypropylene beakers.
Polypropyl. Yes. Any other answers? There can be multiple correct answers also.
So Teflon beakers also.
Yes. So they are using Teflon beakers. Okay. Polypropylene propylene beakers are used in case of acids, but HF specifically actually is generally used in Teflon beakers only. Fine. And Pyrex is clearly no. Glass is clear no. No. Okay. Polypropylene beakers are also not used in case of HF. But if you are going for handling some acid and that also outside the clean room, it can work. But in case of microfabrication, we are going for Teflon beakers only. Fine. Okay. Now remember when Sir started the class, he was talking about something. You might have seen this question also, right? He was talking something about this, the exponential decay in the price of transistors. Okay, so if we let's understand that in sense of a car. Okay, so if we say that a Volkswagen car in 1972, although it was not available in India at that time, right? So uh, like it was of 50 lakhs or 5 million. Okay, and if it is decreasing very similar to the graph you have seen, right, like this, to the price of the transistor, if it would have decreased like that, and that means it should have halved every 1.73 years, how many cars would you will be able to purchase in 1 rupee in 2024? Anyone would like to answer? And there is something like 2 to the power 30 is approximately 10 to the power 9. So any answers for this, or any way we can calculate, like, can anyone give the way we can calculate this? Okay, let me discuss that. Okay, so in total, how many years there has it is 52 years, 1972 to 2024. So 1972 to 2024, that is 52 years. And we are saying that actually every 1.73 years, the price is half, getting half of what it was. Like if it was 50 lakhs, it will cost 25 lakhs after 1.73 years. So we are dividing this 52 by 1.73. And if you divide, you will get approximately 30 point something or 20 point something. Okay. So we can calculate it like 5 uh, 5,000,000 5 into 10 to the power 6 divided by 2 to the power 30, and it was given that 2 to the power 30 is approximately equal to 10 to the power 9. Solving this, we will get like that will cancel out and here 3 will remain. Okay, so 0.005, that will be the cost of one car. So total, if we divide like 1 rupee by this much, we will be able to get 200 cars in 1 rupee. So you can understand, this was just to understand that how the price, like this technology, how much it has evolved. Like if we go like if we see similarly for a transistor, if a single transistor uh, was costing something around 50 lakhs in 1970s, at present it will cost around less than 1 paise, half paise, right? So that is how drastically the prices have decreased, but at the same time the performance have increased. Okay, so let's go to the next question, which is very similar to this but in other terms. That is, a car that had a fuel mileage of 10 kilometer per liter. Yes, are you able to see the slides now?
No, sir.
No? Now?
Now it is. Yes,
Okay.
sir. Yes, sir.
Yes,
Yeah.
sir.
If a car had a fuel mileage of 10 kilometer per liter in 1979, if very similar to the performance of computing performance of the transistors or processors, the mileage would have doubled every 3 years. What would have been the mileage in 2024? Yes, anyone? So total, if we see the difference, 1979 to 2024, it is 45 years, 4.5 decades, right? And it is saying that the mileage doubles every 3 years. So we divide it by 3, so we get 15, right? So it is doubling every 15 years. So 10 multiplied by 2 multiplied by 2, 15 times. Okay, that gives us around 327680. So that is roughly around 3 lakh 30,000 kilometer per liter. So you can appreciate this. These both the numbers are very unrealistic, right? So this is just for you to appreciate that if this transistors and computing have experienced a commendable growth in these years. If a similar growth was available in any other industry, it would have been like the whole scenario of the world would have been different. Okay, and that is why this is hello, hello, am I audible?
Yes, sir.
Okay, yeah. So if a similar growth has been available in case of any other industry, you would have seen a very different world altogether, right? That is why we have to understand like the growth of this industry, microfabrication, whole industry itself. Okay, and it is still growing in terms of like size is shrinking, price is going down, and the performance is increasing. Okay, now let's come to something where we were talking about this impurity in the silicon. Okay, so suppose a device engineer needs metal impurity of less than 10 to the power 12 per centimeter cube. Okay. What is the maximum metal impurity concentration in parts per trillion? So we want it to be very pure. Okay. So we want that it should be less than 10 to the power 12 per centimeter cube. This is still very large, right? 10 to the power 12. That means 10 with 12 zeros. This much metal impurity, but we want less than this. Even for this uh, high impurity, what is the maximum metal impurity concentration that we can allow? Okay, and let's assume the silicon atom density is 5 into 10 to the power 22 per centimeter cube. Yes, anyone would like to do calculation on this? Yes, anyone? Okay, so let me do. So total impurity allowed is 10 to the power 12. Okay, and what is the atomic density? That is 5 into 10 to the power 22. So we want 10 to the power 12 in 5 into 10 to the power 22. And if we do the calculation, we will find that it is 20 ppt, parts per trillion. Okay, billion is 10 to the power 6, trillion is how much? Anyone? Million is 10 to the power 6 or billion is 10 to the power 6.
Sir, million is 10 to the power 6.
Million is 10 to the power 6. So how much is a trillion? 10 to the power 9, right? So if you calculate this, it will come as 1 by 5 into 10 to the power minus 10 equals to around 20 into 10 to the power minus 9. Am I correct? You check the calculation, right? So it will be 20 per 10 to the power 9. That means 20 parts per trillion. Okay. Okay, this is something that we discussed at the beginning. Which substrate you choose for the following application? Epitaxial substrate for visible light, red to green. Okay, LED and photodetectors from gallium arsenide phosphate, indium gallium arsenide, or aluminum gallium arsenide. Okay, so a substrate that we want for a visible light, LED and photodetector, that means to detect different wavelength, okay, of gallium uh, gallium arsenide phosphate or indium gallium arsenide or aluminum gallium arsenide. Okay, the photodetector from this. Then second is growth of blue LEDs, UV detector from gallium nitride and argon. And the third one is wearable or flexible electronics. So what are the options? Glass, silicon, sapphire, PET, sapphire, silicon, gallium arsenide, sapphire, kapton, silicon carbide, germanium, and quartz. Which one will you go for? Yes, anyone? Come on, ask questions. Like if uh, you are able to understand, answer or ask question. That You are not able to understand. See, we talked about, forget about all this. If you just see this, it is flexible electronics, and flexible electronics generally plastic or flexible things are used. Silicon is not flexible, sapphire is not flexible, quartz is not flexible. Only captain is flexible, captain or pet. Okay. Then these materials, gallium arsenide phosphate or indium gallium arsenide or aluminum gallium arsenide, these are grown over gallium arsenide. This can be grown easily over gallium arsenide because you see they also contain gallium arsenide. So if you have a material and on top of it you want to grow a similar crystal, it will be easier, right? That is why this can be a preferred, you can say this can be a preferred material for substrate to grow these materials over them. Then when we are talking about blue LEDs or UV detector, you need a transparent thing. So sapphire will work well for them. Fine. Any questions? Yes. Are you people able to understand? Hello. Hello. Yes. Am I audible? Nitin, Soumya, Nitiraj, anyone?
Yes, sir.
Okay. So
Okay. Next, problem 15. Okay. In the CZ method for manufacturing high purity ingots, segregation coefficient K equals to Cs upon Cl. Cs is impurity in solid and Cl in liquid. So this is the segregation coefficient that we were also talking earlier. Okay. For a given polycrystalline silicon feedstock, that means the starting thing, polycrystalline, with 1 ppm of boron and iron impurity. So we have boron and iron both. Select the correct statement regarding the CZ ingot. So from this stock we melted it, we created the ingot. Fine. So the topmost portion of ingot has boron more than the iron. The topmost portion of ingot has boron less than the iron, or bottommost portion have boron more than iron, or bottommost portion have boron less than iron. Which one is correct? There can be more than one answer. Yes. Anyone? Can anyone answer? Okay. Remember we talked about that dopants have more solubility in the crystal and metals have less solubility in the crystal, right? They are more soluble in the liquid phase. Okay, so you can think that the topmost portion boron will be more compared to iron, because by that time the concentration in the stock itself is high equal for both of them, so boron will be more going more in the crystal. Okay, so the topmost portion that we will get will have boron more, and the reverse will be true for the bottommost portion. So In case of bottommost portion, the boron will be less than the iron, because at that time the concentration of iron will be much more in the stock, and that is why we talked about different grades of wafer that we get. Topmost is the good grade or the prime grade, and the bottommost is the test grade. For the silicon ingots made using CZ process, which of the following statements are true? Diameter of the ingot increases if the pulling rate increases. If we are taking out, like we are rotating and taking out the ingot, right? So if we are doing it fast, the diameter of the ingot will increase. Dopant concentration is constant or almost constant throughout the ingot for a segregation coefficient of K equals to 1. If K, that is Cs upon Cl, is equal to 1 for some material, then the concentration is constant throughout the ingot, or the dopant concentration is constant throughout the ingot for segregation coefficient of K is less than 1. Prime grade wafers are more likely to be obtained from the ending part. Which of these are true? Yes, anyone? Nitin or Soumya? Yes. We just saw that if the dopant concentration is different, then we see different concentration, okay? But if it is 1, in that case we will get the like throughout we will get the same concentration. Then also we discussed that the prime grade wafers are obtained from starting point, not the ending part, okay? So this is correct. Okay, select all the correct statements regarding gallium arsenide ingot production. CZ method, growth of gallium arsenide is difficult as AS evaporates out faster, leaving arsenic deficit melt, okay? It is difficult to make intrinsic or undoped gallium arsenide ingot with CZ method using quartz crucible, as silicon dopes gallium arsenide, okay? CZ method is the method of choice for making gallium arsenide ingots, as it gives low dislocation, or Bridgman-Stockbarger method is the method of choice for making gallium arsenide, as it gives low dislocation density. Which of these are correct? This we have discussed here also, so please answer. Yes, anyone? Remember we discussed that CZ method, in case of CZ method, in the gallium arsenide the arsenic evaporates, and that is why we have a deficit melt, okay? And that is a reason that CZ method is not preferred one for the gallium arsenide, and Bridgman-Stockbarger is the preferred method, okay? So these three are correct. The first one correct, D is correct, and B is also correct, as it is very if you are we are actually putting some materials to stabilize this, don't let the arsenic evaporate, okay? That makes it very difficult to make an undoped gallium arsenide, as well as the quartz crucible of the quartz crucible itself is of silicon, it contains silicon oxide is there, right? So that dopes gallium arsenide, and that is why we are unable to get intrinsic gallium arsenide. Okay. That is a problem with this. And in case of gallium arsenide, we don't want doping like silicon or germanium, because this itself have better conductivity and it has heterojunction properties, and all that will be covered later on. Okay. Select all the statements regarding clean room operations. Subfloor under the perforated main floor makes the airflow more laminar. Okay, so the floor that is under the perforated main floor, okay, that makes the airflow laminar. Okay, okay. Any light can be used where photoresist are stored and photolithography is being done. Addition to gravity force ratio is the same for 0.1 micron and 100 micrometer particles. For similar wafer with similar defect density, the one with higher number of die per millimeter square or number of devices has a better yield. Yes, any answers? Any answer to this?
So as I was talking about the laminar flow, the whole main floor, okay, the perforated main floor makes the airflow laminar. Okay, for similar wafer with similar density, everything higher, if we have higher number of die per millimeter square, it has a better yield. Okay, because we will get less contamination in this case. Okay, now we have talked about DI water. Okay, and we have talked about the conductivity of the DI water also. Okay, so now let's say that an engineer heated a DI water at 80 degrees Celsius to make a cleaning solution. We are talking about DI water at room temperature. That should have a conductivity of 18.6 mega ohm, a resistivity of 18.6 mega ohm centimeter. But this engineer had to make some process in which she had to work at 80 degrees Celsius. Okay. Now, there are more dissociation of water and ions can move faster compared to room temperature. Calculate the expected value of resistivity at this temperature. So, the dissociation of water will happen for H plus and OH minus, right? So, they have different ionic mobility of 0.006 centimeter square per volt second and 0.004 centimeter square per volt second, as well as ionic concentration of both these are 2.89 into 10 to the power 14 per centimeter cube, and we know electronic charge is 1.6 into 10 to the power minus 19 coulomb. So can you calculate based on this? Yes, anyone? At least the formula. Okay, so it will simply be the sum of the ionic mobilities of both the ions multiplied by the this, what you say, sum of the mobility multiplied by the concentration, and the whole thing multiplied by the uh, electronic charge. And if you do the calculations, you will find it to be 2.15 mega ohm centimeter. Fine. Okay, let's discuss the last question. I think we have extended the class a lot, right? So wafers or samples need to be cleaned before processing. Select the correct recipe. Okay. Piranha H to remove native oxide. It etches native oxide, however, it may introduce organic contaminants. HF dip to remove organic residues and particles. SC1 ammonium hydroxide and hydrogen peroxide mixed to remove metal ions. Or SC2 remove alkali and transition metal ions. I think this one everyone should answer. Which one is correct? Is the first one correct? Let me ask someone. Yes, Soumya, uh, Soumya Modlayer, right? Uh, is the first one correct? Nitin, is the first one correct? Speak up. See,
So it's not correct, I think.
yes, it is not correct because we have saw. Let's summarize the whole thing that we have seen. HF dip is used to remove oxide. Piranha removes organic. So we start with Piranha. Then we go for SC1 that is used to remove particles from substrate. Okay. Due to the pH of the solution, the particle removed from the surface are more likely to stay in the solution and do not redeposit on the wafer surface. And then comes the SC2 that is to remove alkali and transition metal ions. So metal ions are removed by HF is done at the last because SC1 leaves a oxide layer on the top and that is removed by the HF dip. So the only correct answer in this case will be the D, that is SC2 that removes alkali and transition metal ions. Fine. Okay. Any questions after this? Hello?
No, sir.
No? Okay. You can even write the details, and this lecture will also be available in the, like, will be shared in the YouTube. So you can check there, and the slides I will post. Okay. So the next topic, that is week 2, will be the additive processes, defect and diffusion. And my this live interactive session will remain at the same time, that is 7 p.m. on Tuesday. The same link will be there. So that's all. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, everyone.